Hello everyone, this is Vasishta from Aerobee section. Today I am going to explain a topic about composite beams of analysis of aircraft structure. So coming to the topics that are related to composite beams, I have made these things like introduction, axial loads, moment loads, bending stress. So introduction part. As we know that the beams that are constructed using more than one different material, two or more different materials are called as composite beams. Actually, composite is a material which is a mixture of two or more different materials. The composite, the examples of composite materials are like carbon fiber, fiberglass, etc. So the beams are made out of composites. The composite beams are designed to develop a most efficient mean for carrying applied loads. Like there are some type of beams like a composite I-beam section, double pipe beam section, and stack beam section. These are the composite beams. In I section, there will be two types of materials. The upper part and the lower part will be the same material, and the part which is in the middle will be a different material. The mixture of this will become a composite beam, composite I section beam, and the double pipe beam consists of a outer diameter of another material and inner diameter of another material, which becomes a composite double pipe beam composite and stacked beams. The stacked beams are the commonly seen composite materials like the materials one material and the second material will be stacked up and they become the beam. The simplest load in composite beam is axial load. The strain is across the beam cross section, but the stress is discontinuous as shown in the figure. When This is a figure which has a strain and the axial stresses which are acting on the composite beam. This when axially loaded, the normal strains are equal to the materials are rigidly attached. Ep- Epsilon 1 is equal to epsilon is equal to stress by E, sigma 1 by E1, and E2 is equal to E is equal to sigma 2 by E2. Eliminating sigma gives sigma 1 by E2, E1 is equal to sigma 2 by E2. The total load P must be equal to stresses times that respective area are. P is equal to A1 sigma 1 plus A2 sigma 2. Combining the previous two equations, we get sigma A1 is equal to P by A1 plus A2, E2 by E1, and sigma A2 is equal to P by A1 into E1 minus E1 by E2 plus A2. So this is a diagram related to the composite beams, the stress and strain of a composite beams under axial loads. Coming to another topic, the moment load. Similar to axially loaded two material beams, we have a beam when a beam is subjected to moment, the strain is still continuous, but the stress is discontinuous, where the strain and the stress and strain in the axial load is constant. The the bending strain and stress is a linear function through the thickness for each material shown as in figure 3. In this figure, we can see that the composite beams are under the moment loads. So there's a topic in the moment load which is the neutral axis. As with the non-composite beams, the neutral axis is the location where the bending stress is zero. The location of the neutral axis depends on the relative stiffness and size of each of the material section. Generally, the NA location, neutral axis location, is determined relative to the bottom surface of the beam. However, this is not mandatory, and the location can be relative to any location. If the bottom is used, then the neutral axis is distance h from the bottom as shown in the figure diagram. As the distance h can be determined by recalling the stresses through the cross section must be in equilibrium, summing the forces in the x direction gives. In the diagram 4, we can see that in this diagram 4, we can see the neutral axis of composite beams. The where the location at which the bending stress will be zero. So here is a formula regarding this neutral axis. Sigma fx is equal to 0. Integration of sigma b dA, that is equal to integration of a1 sigma b1 b minus 1 dA plus a2 sigma b minus 2 dA. The bending stress in the any B section related to the radius of curvature rho as sigma is equal to minus c by y by rho. 0 is equal to a1 0 minus e1 y1 by p dA plus a2 minus sigma integration of a2 minus e2 y2 by rho dA. Since the curvature is the same at all locations of the given cross section, the equation simplifies to 0 is equal to e1 integration of a1 y1 dA plus e2 integration of a2 y2 dA. The two integral the two integrals are the first moment of each material area, which is commonly noted as simply q, giving 0 is equal to e1 q1 plus e2 q2. Coming to another topic, bending stress. Bending stress in a composite beam is founded by using moment equilibrium. At any internal location summing the moment, sigma mz is equal to 0. This is the inner location of composite beam, which is the neutral axis, where the bending stress is 0. Sigma mz is equal to integration of yb sigma by dA plus m. That is equal to m plus integration of a1 sigma b1 minus 1 y dA plus a2 sigma b minus 2 y dA. Using the relationship between the bending stress and the radius of curvature, sigma is equal to using the relationship between the bending stress and the radius of curvature, sigma is equal to Ey minus Ey by P rho, which gives m is equal to E1 by rho integration of A1 y square dA plus A2 by rho A2 y square dA. By noticing the integral in the second moment of the area, which is also area of momentum, which simplifies to m is equal to E1 by rho L1 plus E2 by rho L2. So these are the stresses that are acting on the composite beams, like a composite beam with which is undergoing types of loads and what is what. Mostly in aerospace field or aeronautical field, we use composite structures like a composite beam for the spars and spindles for the aircraft will be much more helpful for reduction of weight and to strengthen the aircraft. Now taking this reference from an online, which consists of courses with the composite beams. This is a reference that I have taken from the composite beams. from an engineered beams data. This is all for my explanation. Thank you.